Okay, in this video we'll be going through the 2015 Scholarship Physics exam. Describe the photoelectric effect. In your answer, you should include a derivation of the relationship between the incident photon frequency and the electron's kinetic energy, and how these relate to the work function of the metal. The photoelectric effect is when electrons are released from a metal surface when photons of sufficient energy hit the metal surface. If the photon does not have sufficient energy, then no electrons are released at the energetic threshold, which is the minimum amount of energy needed to release an electron, aka the work function. Then electrons are released with 0 EK. Thus, the kinetic energy of an electron is equal to the energy of the incident photon minus the energy needed to release the electron. Again, that is the work function. Thus, we get the equation EK is equal to HF, which is the energy of the incident photon, minus phi, which is the work function. The photoelectric effect was unable to be fully explained using classical physics. Comment on this statement. So there are three main points where classical physics could not explain the photoelectric effect. The first one being the threshold frequency. So in classical physics, there was thought to be no threshold frequency at which electrons could be emitted. They thought that electrons could be emitted at all frequencies. The next is the energy of the released electrons. They thought that the energy of the electrons will be related to the intensity of the light rather than the frequency. They thought it may take some time for the energy to build to a sufficient value until electrons are emitted. However, in reality, electrons are emitted instantaneously as long as the threshold frequency is met. So we can write those three in. According to classical theory, there should be no minimum frequency of which electrons are released, as energy of the light is dependent on the intensity, assuming that light purely behaves as a wave. However, we know that below a certain frequency, which is the threshold frequency, no electrons are emitted regardless of the intensity of the light. So now for the energy of ejected electrons. In classical theory, light is treated as a continuous wave, and the energy of the wave depends on the intensity, which is the amplitude or the brightness of light. Therefore, we would expect that increasing the intensity of the light would result in electrons being ejected with more energy. However, the energy of emitted electrons actually depends on the frequency of the light. Thus, no electrons are emitted below a certain frequency regardless of the intensity of the light. This is again the threshold frequency. Okay, so now moving on to instantaneous emission. Classical theory would also predict that if light were a continuous wave, electrons will be ejected after some time delay, as the energy of the wave will accumulate over time. However, in reality, electrons are emitted instantaneously when exposed to light above the threshold frequency. So as you can see, in all three cases, there are some crossovers with the fact that energy does not come from the amplitude of the light or the intensity of the light. Instead, the energy of the photons are directly related to the frequency, and this is what causes the electrons to be emitted. Okay, sweet as. Describe the similarities and differences between the orbit of the moon around the Earth and the orbit of an electron around a proton in a hydrogen atom. Okay, so in both cases, they both experience a centripetal force, which is directly proportional to the square of the radius between the two center of masses. And in both cases, they both orbit around the center of mass of the entire system. That's a key distinction. The moon does not orbit around the center of mass of Earth. It orbits around the center of mass of both the Earth and the moon. However, as the Earth is way bigger than the moon, the center of mass of the system is still within Earth. And the same goes for the proton and the electron in the hydrogen atom. As the proton is much more massive than the electron, the center of mass of the system is still within that proton. So for the similarities, both experience a centripetal force, which is proportional to the square of the radius of the orbit. As you can see there, I've provided the two equations, and you can see they both have r squared in the equations. Both also orbit around the center of mass of the system, not the center of mass of the more massive object. That is a key distinction. So now for the differences, the centripetal force in the hydrogen atom is supplied by the electrostatic attraction between the proton and the electron, whereas the centripetal force between the moon and the Earth is provided by the gravitational force between the Earth and the moon. Another difference is the electrons' orbits are quantized, meaning they are limited to specific values, whereas on the other hand, the possible orbital radius of the moon is effectively continuous. This does not mean that the moon doesn't have quantized values, but it's more so that the quantized values of the moon's orbit are too small to perceive relative to the size of the orbital radius. Sound from a small speaker L reaches a point P by two paths, which differ in length by 1.2 meters. When the frequency of the sound is gradually increased, the resultant intensity at point P goes through a series of maxima and minima. A maximum occurs when the frequency is 1000 Hz, and the next maximum occurs at 1200 Hz. Explain what causes the maxima and minima to occur. Okay, so there is a lot to go through here. First, we're going to establish what causes a maximum and minima. This is just standard level 3. The interference of the sound waves from these two paths causes the intensity at point P to fluctuate between maxima and minima. This is because the waves either constructively or destructively interfere depending on the path difference between them. When the path difference is a whole number of wavelengths, the waves arrive in phase, thus resulting in constructive interference, thus forming a maxima. However, when the path difference is a non-whole number of wavelengths, aka like n.5, the waves then arrive out of phase, thus resulting in destructive interference, thus a minima is produced. Okay, so this is what, this is the scholarship part, which requires deeper thinking. Due to V is equal to F lambda, as frequency increases, then lambda must decrease, as the speed of sound is constant. Thus, as the path difference is equal to n lambda, so that is our PD is equal to n lambda. As the path difference is constant, so this is constant at 1.2 meters, then if our wavelength decreases, then the only thing that can change is our n multiple. And so our n multiple is going to go through a series of whole values and non-whole values, which causes the maxima and minima. So n is going to fluctuate between 1.1, 1.2, and then eventually 1.5, and then it's going to go to 2, and then 2.1, and then 2.2. So this n value is going to change as our lambda decreases, and that's what's going to cause the series of maxima and minima. Calculate the speed of sound in the medium between L and P. So to find the speed of sound, we know that's equal to F lambda. Now at the lowest frequency that causes the first ever maxima, our path difference is going to equal to lambda. This is because n is equal to 1 at this point, so 1 lambda is just lambda. And so we know our path difference is 1.2, and therefore our wavelength is 1.2 meters. So the lowest frequency, which causes a maxima, we can observe up here. In this question, we can see that there is 200 Hz between each maxima, right here. And so we can observe that the lowest frequency that's going to cause a maxima is going to be 200 Hz, because every 200 Hz there is another maxima. So the next maximum will be 400 Hz, and then 800 Hz, and then we have our 1000 Hz, and then our 1200 Hz. So the lowest frequency that's going to cause a maxima is our 200 Hz. So we also know that our frequency is 200 Hz, and so we can plug that in, as V is equal to 200 times 1.2, and this gives us a velocity of 240 meters per second. There we go. A small ball of mass m hangs from a light inextensible string attached to a fixed horizontal post of radius r1, as shown. The ball is hit horizontally with a large bat so that the ball wraps around the post. Show that the ball's speed at the top of its first swing must be at least that equation there, so the string remains taut. Okay, so the ball is hit this way, and therefore if we have our post again, when it's hit, the ball is going to wrap around, and therefore at the end position, the rope is going to look something like this at its max height, like that, and we have the mass m over here, and this has a radius of r1. So this total distance right here is r2, right? That's that same distance over here, and we can call this distance here our x. So what we want is the minimum speed so that the string remains taut. The reason why we want the minimum speed is because it says the first swing must at least be this equation here. So at least meaning the least, the lowest value. So that implies a minimum speed. So in a vertical circle, the minimum speed is where the centripetal force is equal to the weight force. And therefore our mv squared over r is equal to our mg. These masses can cancel out, and v squared over r is equal to g. And therefore our velocity is equal to square root gr. Now, as you can see, in this case, our radius is actually our x value, so we can sub that in, where our velocity is our square root gx. As you can see, we've gotten pretty close already, but as you can see, our x value is that right there, and it's in terms of r1 and r2. So we have our r2, which is our total distance, which is here, but some of the rope is wrapped around the post. So our x is at least r2 minus a certain value. This rope wraps around 1/4 of the post circumference. The circumference of a circle is 2 pi r, and therefore 1/4 of that is 2 pi r over 4, or pi r over 2. The radius of this is r1, and so that's pi r1 over 2. And therefore our x value is our r2 minus our pi r1 over 2. Subbing that in, we get the equation that we are trying to find. There we go. For the speed of the ball in A, show that the initial speed must be at least that equation there. Okay, so for this question, we can use our conservation of energy. If we have our scenario initially, and we have our scenario finally, at this point here, just after the ball is being hit, all the energy is going to be in terms of EK. However, up here, the ball is going to still have some EK, which will make it continue to wrap around, but it's at its highest position, and therefore there is some EP, gravitational potential energy. And so we can write that as our equation. The EK initially is equal to the EK finally plus gravitational potential energy. Therefore, our half mvi squared is equal to half mvf squared plus mgh. Now we can cancel out our masses, and we get half vi squared is equal to half vf squared plus gh. Timesing both sides by 2 to get rid of the halves, we get vi squared is equal to vf squared plus 2gh. Now in the previous question, we found out our final velocity is this equation right here, so we can make that substitution. Vi squared is equal to square root g r2 minus pi r1 all over 2 squared. Now as we have a square root within a square, we can just get rid of those two, like so, and that's plus 2gh. Okay, so we can no longer go any further with the simplification, so now let's find out our h value. If we go back to our diagrams, the h value is the total change in height of the ball. So if we, in this diagram, put our before state as a dotted line, like this is going to be our h. We know that this distance here is r2, and we also know that this distance here is our x, which we defined before. And now this gap right here is our radius of the pole, which is r1. And so therefore, our height is equal to r2 plus r1 plus our x value. Now our x value is what we defined before, which is this right here. And so we can sub that in. Simplifying this. Now we can make this substitution. 2r2 plus r1 minus pi r1 over 2. There we go. So now we can expand this out, and we get vi squared is equal to gr2 minus g pi r1 all over 2 plus 4gr2 plus 2gr1 minus 2g pi r1 all over 2. So we can cancel out these 2's to simplify it further. Now gathering our like terms, as we have g as a common factor in all three of these, we can take it out. Also, as r1 is a common factor between these two terms, we can take it out also. And we get vi squared is equal to g 5r2 minus 3 pi over 2 minus 2 r1. And now we can square root both sides to get rid of this square, and we get the initial velocity is equal to g5r2 minus 3 pi over 2 minus 2r1, and that is our final equation. And as you can see, that is the equation that we're trying to find. Assuming an elastic collision, show that the speed of the bat is approximately half that of the ball's initial speed. State any other assumptions you made and the reasons for them. So first things first, let's do our conservation of momentum. So our initial momentum, the only thing that's moving is the bat, so the mass of the bat times the velocity of the bat. And for our final momentum, the bat after you hit the ball is still going to be swinging, right? You don't just hit the ball and stop. So the bat is still going to have momentum and the ball is also going to have momentum. So we have the mass of the ball again times the velocity of the ball. I'm going to call this VB2 because when you hit the ball, the bat is going to slow down ever so slightly. And so those are two distinct velocities, plus the velocity of the ball. So for the mass of the ball, I'm going to use little b times the velocity of the ball, again, little b. So b is equal to ball, and big B is equal to bat. There we go. Now we can gather our like terms and move this onto the side, taking out mb as a common factor. And we can divide both sides by mb, and we get vb minus vb2 is equal to m little b times v little b all over mb. Okay, so we're going to leave our conservation of momentum right there, so let's move on to our conservation of energy. Again, initially the only thing that's moving is going to be the bat, so that's going to have all the kinetic energy in the system, so that's half mass of the bat times velocity of the bat squared. And for our final energies, the bat is again still going to be moving, so that's half mb vb2 squared plus our kinetic energy of the ball, which is half mb vb squared. Timesing both sides by 2, we get mb vb squared is equal to mb vb2 squared plus m little b v little b squared. Gathering our like terms, we can move this onto this side, and we get mb vb squared minus m b vb2 squared is equal to m little b v little b squared. Taking out mb as a common factor, and we can also divide both sides by m little b. That way we have the velocity of the ball on its own. Now we can expand this out, and we get mb over m little b, vb minus vb2, and then vb plus vb2. And that's all equal to v little b squared. Now, as you can see, this term is equal to this right here, and so we can make that substitution. So now, as you can see, this mb cancels out with this mb right here, and this m big B cancels out with this m big B right here. And so therefore, our v little b times our vb plus vb2 is equal to vb squared. Now we can divide both sides by vb, like so, and this power cancels. Therefore, our vb plus vb2 is equal to the velocity of the ball. Now, an assumption that we're going to make is that after the ball has been hit, the bat doesn't slow down very much. You can imagine if you hit a ball with a bat, when you hit it, you can't really feel the ball being slowed down that much. So we can make the assumption that vb is equal to vb2, and therefore 2vb is equal to the velocity of the ball. And therefore the velocity of the bat is equal to half the velocity of the ball, which is what we are trying to find. There we go. As the ball completes its first orbit around the post, explain why the ball appears to be traveling at a greater speed than its initial value. Okay, so as you can imagine, as the ball keeps on wrapping around the post, the effective radius is decreasing, and therefore as I is equal to mr squared, if the radius is decreasing, then the rotational inertia must decrease as well. And as angular momentum is conserved, if I decreases, then the angular velocity must increase. And therefore, as the angular velocity increases, the speed of the ball will increase. And so we can write that in. The radius is decreasing, thus the rotational inertia must also decrease as the mass is closer to the axis of rotation. Thus, as angular momentum is conserved, angular velocity must increase proportionally, thus the ball will appear to be moving faster. Show that the range r of a projectile thrown from the ground level at angle phi to the horizontal with a starting velocity v is that equation there. So this is the range equation. I have made a video on that on my channel. It's in deriving formula. I think it's like 6 minutes in or so, but I'll still go through it in this video as well. So if we have a projectile thrown, there is going to be a range, which is our r. This is our range r, which is another word for our horizontal distance. And if we throw the ball, there's going to be a velocity v, and that's at an angle phi to the ground. Now if we take out this velocity and we break it up into its components, we can say that this is v and this is v cos theta, or in this case phi, and this is v sine phi, as this angle right here is our phi. Now we know our velocity is equal to distance over time, and therefore our distance, which is our horizontal distance, which is our r, is equal to velocity times time, and therefore our range, which is our horizontal distance, is equal to the horizontal velocity, v cos phi, times our time. So we have the first part of the equation. Now we need to find what the hell t is equal to. Now in order to do that, we can use our kinematics. Total horizontal time is equal to the total vertical time, right? Because that's just how long the ball is in the air for. So we can use our distance is equal to vit plus half at squared. As this is velocity in the vertical direction, our vi is going to be our v sine phi. And also, our acceleration is going to be negative g. So we can minus half g t squared. Now, as you can see, this is looking like a quadratic where we have our t squared and our t. This makes sense because a projectile follows the path of a parabola. So we can make this equal to 0. And we can take out t as a common factor. Now, as you can see, there are two solutions. This solution will be when t is equal to 0. This makes sense as this is this part of the motion. So when t is equal to 0, it's going to be at the beginning. However, we're looking for when the ball is at this position, so we're wondering what that t value is. And so v sine phi minus half gt is equal to 0, and therefore v sine phi is equal to half gt, and therefore 2v sine phi over g is equal to our time. So now we can make that substitution. Our range is equal to v cos phi times 2v sine phi all over g. Now, understanding our trig identity up here, we have that trig identity within here. And so our range is equal to v squared, which is v times v, sine 2 phi all over g. And as you can see, that is the equation that we're trying to find. A cricket ball is thrown from ground level with a velocity of 28 meters per second and hits a target 80 meters away. Show that the time of the flight of the ball is 4.04 seconds. The effects of air resistance can be ignored. So for the flight time, again, as I said before, the total vertical time is equal to the horizontal time. So we can just use our v is equal to distance over time, and therefore our time is our distance all over our velocity. We know our distance is 80 meters. However, we don't know the value of our velocity. We know that our velocity in the horizontal direction is v cos phi, where our v is 28 meters per second, but we don't know our angle. We know our range equation is equal to v squared sine 2 phi all over g, and therefore our g over v squared is equal to sine 2 phi, and therefore the inverse sine of r g over v squared is equal to 2 phi. Now plugging in our numbers, our r is our total range, which is our 80 meters. times g, which is 9.81, all over our v squared, which is 28 squared, and that's equal to half pi. Now, as that is 2 times our angle, to find phi by itself, we divide half pi by 2, and that's equal to 1/4 pi. And therefore, our horizontal velocity is equal to 28 cos 1/4 pi. So we can make that substitution. Our distance is again 80 meters divided by 28 cos 1/4 pi. And that gives us a time of 4.04 seconds. As you can see, that is the time that we're trying to find. The ball is now thrown at the same target with the same initial speed but at a lower angle. This time it is aimed to bounce in front of the target so that it hits the target on the second bounce. When the ball bounces the first time, it rebounds with the same angle as it came in, but loses half its speed. Calculate the time taken for the ball to reach its target. So now during this situation, we have a ball being thrown, it bounces on the ground, and it hits the target on the second bounce. So we can call this distance here R1, and this distance here R2, and this is going to be our total range. So therefore, our total is equal to R1 plus R2. As we know, our total range is 80 meters. We know our range equation is equal to v squared sine 2 phi all over g. Our velocity for the first throw is 28 squared sine 2 phi all over 9.81. And our R2, we know that's 14 squared. The reason for that is because it loses half its speed. Sine 2 phi, that is the exact same angle, divided by 9.81. Now, timesing both sides by 9.81, we get 784.8 is equal to 28 squared sine 2 phi plus 14 squared sine 2 phi. As we have sine 2 phi as a common factor, we can take it out. And now we can divide both sides by 28 squared plus 14 squared. And that's equal to sine 2 phi. Therefore, the inverse sine of 784.8 divided by 28 squared plus 14 squared is equal to 2 phi. And this gives a value of 0.93 radians. Now, as that is 2 phi, dividing this by 2, this gives us a value for phi as 0.46 radians. Okay, so now that we know our angle, we can sub that into our R1. So our R1 is equal to 28 squared sine 2 times 0.46 all over 9.81. And this gives us a value of 64 meters. And therefore, as our RT is equal to R1 plus R2, our 80 meters is equal to 64 plus R2. Therefore, our R2 is equal to 16 meters. Now again, as our velocity is distance over time, our time is our distance over our velocity. We can define T1 as the time taken for the ball to travel the distance R1, and our T2 as the time taken for the ball to travel distance R2. So our R1 is equal to our 64 meters divided by 28 cos 0.46 radians. This gives us a total time of 2.556 seconds. Our T2 is equal to 16 divided by 14 cos 0.46, and this gives us a total time of 1.278 seconds. Therefore, our total time is equal to T1 plus T2, and therefore our total time is equal to 2.556 plus 1.278, and that gives us a total time of 3.834 seconds. There we go. Discuss with physical reasons the differences in times between part B and part CI. So because the second throw in part C has a lower release angle, in order to travel the same distance, there must be a higher horizontal velocity. And therefore, as velocity increases, then time decreases as they are inversely proportional, and because the distance total stays the same at 80 meters. So we can write that in. As the second throw has a lower release angle, it must have a greater horizontal velocity. This therefore results in a shorter total time, despite the loss in speed due to the bounce. Any real throw of a ball will be approximately at head height, rather than from the ground. Show that the range achieved by a throw from a height 2 meters above the ground would be that equation there. So if we map that out, we have our guy right here. He throws a ball from approximately head height, which is 2 meters apparently, so he throws the ball right here. And that's going to follow a projectile, and it's going to hit the ground. Now, as you can see, this is not symmetrical, so the time taken for the ball to reach max height, which we can call t up, and the time taken to go down is not going to be the same because they are not symmetrical on both sides. So the best way to approach this, I believe, is to mark this as if this is the ground, so above head height. So for the first half, we treat it as a regular parabola, and then for the second half, we can mirror whatever this value is, and then we plus 2 meters at the end, right? Because that is going to be 2 meters over there. So in order to get the time taken to travel up, we can say that Vf is equal to Vi plus At. Now at its peak position, we know that velocity is equal to 0 at this point, and we also know that our acceleration is equal to negative g, and so therefore 0 is equal to Vi minus gt, and therefore gt is equal to Vi. So our time is our velocity initially all over our g. Now, as stated in the first question, our vertical velocity is v sine phi, so we can make that substitution for our Vi. So our t is equal to v sine phi all over g. Okay, so now that we have the time, we can find this total distance right here, so this top half without the bottom part. And to do that, we can use our distance as velocity initially times time plus our half at squared. Now again, we know our acceleration is negative g, and our velocity initially is our v sine phi, and we just found out our time as v sine phi over g, so we can make those substitutions right here. So first of all, simplifying this squared, we can get rid of the squared up here, and we can change that to v squared sine squared phi over g squared. And then right off the bat, you can see we can cancel out this g with this power. And we can also see that this is going to be v squared sine squared phi as well. So we can make those changes as well. Now we have this right here. As you can see, we have a whole minus a half. So if we have 1 minus 0.5, that's just going to equal 0.5. And so as you can see, this is going to equal to half v squared sine squared phi all over g. Now we can simplify this to just be v squared sine squared phi all over 2g, right? There we go. Now again, that is this distance traveled right here. So our total distance, the total is going to equal to this distance right here, plus our 2 meters at the end. So that is going to be v squared sine squared phi all over 2g plus 2. So now in order to find the total time down, we can use the equation d is equal to half gt squared. Now the reason why we have negated vit is because we do not have an initial velocity, and therefore that cancels out. And so from there we can rearrange, so our t is equal to the square root of the distance over our g. Now this distance here is our d total, which we just found, so we can make that substitution. So our t down is equal to the square root of 2 times v squared sine squared phi over 2g plus 2 all over our g. Now this 2 cancels out with this 2 right here, and we get our t down is equal to the square root of v squared sine squared phi all over g squared plus 4 over g. So this g squared comes from this g and this g, and the 4 becomes from this 2 timesing with this 2 right here, and this g is all over everything, so we just move that over there. And so our total time is equal to the time up plus the time down, and therefore our time up was v sine phi over g, and our time down, which we just found, is square root v squared sine squared phi over g squared plus 4 over g. And so this can be simplified as v sine phi plus square root v squared sine phi plus 4g all over g. Okay, so finally now we have our total time. And so again, we know our velocity is equal to distance over time. So now to find our total distance, that is velocity times time. We know the velocity in the horizontal direction is v cos phi, and we know our time, which we just found. And so our distance is equal to v cos phi times v sine phi plus square root v squared sine squared phi plus 4g all over g. And as you can see, this is the equation that we are trying to find. There we go. Okay, question 4. In the circuit shown, the switch is closed at time t is equal to 0. Write an expression for the current immediately after the switch is closed, and explain your reasoning. Okay, so immediately after the switch is closed, there is going to be a high rate of change of current, and therefore there is going to be a high rate of change of flux, and therefore there is going to be a high back EMF produced by the inductor. This EMF is going to be equal to the voltage of the battery of the source, and therefore this side of the circuit is going to be effectively cut off for that brief period of time. And as you can see, this is just going to be a regular series circuit, and therefore the current is going to be equal to the supply voltage all over the total resistance, which in this case is just R, and so the current is going to be V over R. Write an expression for the limiting value of the current a long time after the switch is closed. Explain your reasoning. Okay, so this is a long time after the switch is closed, and therefore the inductor is effectively just a regular wire, and so the reactance of the inductor is 0, and therefore the total resistance is going to be these two resistors only. As these two resistors are in parallel, that's going to be 1 over R plus 1 over R, and that's all to the inverse, and therefore the total resistance is equal to R over 2. And therefore, again, as the current is equal to the source voltage all over the total resistance, the current is going to be equal to V over R divided by 2, which is equal to 2V over R. There we go. A charged capacitor is connected to an inductor, as shown in the diagram below. When the switch is closed at time is equal to 0, the current in the circuit will oscillate with a period of 6.28 seconds. Describe the energy changes that take place in the course of one complete cycle. Okay, so this is a case of simple harmonic motion, where the charge is going to oscillate between the two capacitor plates, like so. So what's going to happen is the current is going to rise slowly up until the point when the rate of change of current is 0, and therefore there's no more back EMF produced by the inductor, and at this point the current is going to be max. When the current is max, there is going to be max flow onto this side of the capacitor, and as charge begins to build up onto this side of the capacitor, there is going to be more positive charge, and therefore as more positive charge begins to flow, there is going to be a repulsive force pushing it back, and therefore the current will begin to slow down again, and as the current begins to slow down, there is going to be a rate of change of current, and therefore the inductor is not going to like that again. Because the inductor wants to keep things the same, it's going to try push the current even more, thus forcing all the positive charge onto this side of the plate, leaving this side completely negative now. And then at that point, the cycle happens in reverse. And this side will become positive, and then this side will be the negative side. The positive charge on the capacitor will attempt to move through the circuit in order to discharge itself. As the capacitor attempts to discharge itself, there is going to be a high rate of change of current, thus there is going to be a high rate of change of flux, thus the inductor is going to produce a back EMF that opposes the oncoming current. This causes the current to rise slowly. After some time, the current will reach a max value. At this point, the back EMF is completely gone, and therefore the current begins to flow onto the other plate of the capacitor. Thus, due to repulsive electrostatic forces, the current will slow down again as it becomes harder for charge to accumulate onto the other plate. Therefore, as current is once again changing, the inductor will try to prevent this change and maintain the max current, thus forcing the charge onto the other capacitor plate. Then the process reverses itself. Thus, due to the above, electrical potential energy stored in the capacitor converts itself into magnetic field energy by way of current. This magnetic field energy then converts into more current, thus driving charge onto the plate of the capacitor, thus restoring the electrical potential energy. This process repeats itself again. So it does. The capacitor plates can be moved closer together so that the capacitance is increased to 4 farads. Explain at what point in the cycle could the plates of the capacitor be moved closer together so that no energy is transferred into the circuit. Okay, so if we imagine each cycle of the simple harmonic motion of the circuit as a sine wave, right? Let's draw that better. There we go, that should be good enough. This right here, this distance right here, that's 1 period, right? And so 1 period in this is where it goes over here, and then it comes back. So that's 1 period. Divide each section into quarters, right? Like this. This first quarter right here, that is when all the energy from the capacitor is now in the inductor. The second part here is when this energy from the inductor comes back onto the other side of the capacitor. And this part right here is when it goes back into reverse, back into the inductor. And this part right here is when the energy goes back onto the capacitor. And so as you can see, the first quarter is when there is no charge separation on the capacitor, and therefore there is no energy stored in the capacitor. And so the first quarter of the cycle is the best time to do this. So we can write that in. At 1 quarter of the period, the capacitor plates can be moved closer together without transferring energy. At this point in the cycle, the capacitor has completely discharged, thus there is no voltage across the plates. As a result, no energy is stored in the capacitor at this moment, as all the energy is in the magnetic field of the inductor. Thus, no work needs to be done when moving the plates closer together. A slab of copper falls freely under the influence of gravity before entering the region between the poles of a strong magnet. As it enters the magnetic field, the copper slab slows down. Explain why this occurs and state what happens to the kinetic energy of the copper slab. Okay, so as the copper slab falls down through the magnetic field, there is going to be a change of flux in the copper slab, thus producing a back EMF. That's due to Faraday's law. This back EMF is going to produce eddy currents. These eddy currents produce a magnetic field in such a way that opposes the permanent magnetic field. This is Lenz's law, and therefore this slows down the copper slab. So we can write that in. As the copper slab falls, it enters the magnetic field, which causes a change in flux. This change in flux will induce a back EMF due to Faraday's law. This back EMF will produce eddy currents. These eddy currents produce their own magnetic field, and due to Lenz's law, these eddy currents are produced in such a way that their magnetic field they generate opposes the permanent magnetic field. This results in a magnetic force which opposes the copper slab motion, thus slowing it down. Therefore, the kinetic energy in the copper slab is converted into heat due to resistance. Okay, question 5. The speed of a wave on a string is given by that equation there, where T is the tension on the string and mu is the mass per unit length, measured in kgs per meter. Show that the equation above is dimensionally correct. Okay, so dimensionally our velocity is equal to meters per second. And so if the square root of tension over mass per unit length is equal to meters per second, then we know it's dimensionally correct. So we know that tension is a force, so we can use any force equation. Let's use F is equal to ma, and therefore dimensionally a force is equal to kg meters per second. Mass per unit length dimensionally is kg per meter, and so kg meters per second over kg per meter. The kg's cancel out, and we're left with meters squared per second squared. Now, as this is all over a square root, we can square root this, and this gives us meters per second, which means that this equation is dimensionally correct. There we go. One end of a string of mass per unit length mu is attached to a solid wall, while the other end passes over a pulley and is attached to a hanging mass m, as shown in figure 1. A second string of the same length and made of the same material but with twice the diameter is mounted with a similar fashion with an identical mass m, as shown in figure 2. The first string oscillates in its first harmonic when driven at a frequency of 200 Hz. Calculate the frequency that would cause the second string to oscillate at its third harmonic. So for figure 1, our V1 is equal to the square root of our T1 over our mu1. So we're labeling 1 for figure 1 and we'll label 2 for figure 2. Therefore, as our tension force is just the force of gravity from this mass, we can replace that over here and get V1 is equal to m1g all over mu1. Now, as the first string is oscillating at the first harmonic and we have nodes on both ends, we know that the length is equal to lambda over 2, and therefore the wavelength in figure 1 is equal to 2L. We also know that V1 is equal to F1 lambda 1, and so therefore V1 is equal to 2L F1. So therefore 2L F1 is equal to the square root of m1g all over mu1. So we can leave that here for now and let's move on to figure 2. So V2 is equal to the square root of T2 all over mu2. As we're dealing with the third harmonic, we know the length is equal to 3 over 2 lambda 2. Lambda 2 meaning the wavelength of the second figure. And so therefore the wavelength of figure 2 is equal to 2L over 3. And therefore, using the same process over here, we know that V1 is equal to 2 over 3 LF2. Therefore, 2 over 3 LF2 is equal to square root m2g all over mu2. Now again, m2g comes from that the tension force is produced by the weight force of the mass. So the key idea here is that in the second figure, the string has twice the diameter and therefore it also has twice the radius. So this is going to affect the mass per unit length. So we know that mass per unit length dimensionally is kgs per meter. We know that one way we can calculate mass per unit length. And so looking at this, one way we can calculate the mass of a string is by taking the density, timesing it by the area, timesing by the length. And this equals the mass. Now the reason for this is because density is kg per meter cubed times by our area, which is meters squared, times by length, which is meters. And as you can see, the masses will cancel and we're just left with kilograms. And so therefore, as mu is mass per unit length, this is going to be our density times by our meters squared times by our meter all over our length, right? Kg per meter. So we know that this is kg per meter, and as you can see, this meter will cancel out with this meter, and so as you can see, our mu is effectively just kg meter cubed times our meters squared, and dimensionally this still does equal kg per meter, you can see. And so coming back, we know that our diameter doubles, right? Twice the diameter right here, and therefore if diameter doubles, and therefore radius must also 2x, right? And so we know that in a string, if we take the cross section, that's just a circle. The area of a circle is pi r squared. So if radius doubles, that means the area must 4x, right? Because radius is squared. So therefore, if the area increases by 4x, therefore mass per unit length must also increase by 4x, because the density remains the same. And therefore the mass per unit length in figure 2 is 4 times the mass per unit length in figure 1. So we can replace this with 4 mu1. Now as you can see, if we compare this and compare this, now if we compare this right here to this right here, we can see that this is double than this. So therefore half of square root m1g all over mu1 is equal to the square root of m2g all over 4 mu1. Now as we can see up here, both masses have the same exact value, so m1 is equal to m2, and so if we divide this by 2 we get this right here because everything else is the same, and so therefore half of this is equal to this. So half of 2 LF1 is equal to 2 over 3 LF2, and therefore LF1 is equal to 2 over 3 LF2. Cancelling out our L's, we get F1 is equal to 2 over 3 F2, and therefore 3 F1 over 2 is equal to F2. We know that F1 is equal to 200 Hertz, and therefore 3 times 200 all over 2 is equal to F2, and thus 300 Hertz is equal to F2. There we go. Now the first string is hung so that both ends go over pulleys with the masses suspended at each end, shown in figure 3. Calculate the frequency of the fifth harmonic. So the tension will remain the same, and therefore the velocity of the wave will also remain the same, and as v is equal to f lambda, everything else will remain constant. And in order to calculate the first harmonic, we take the frequency of the first harmonic, which is 200 Hertz, and we times that by 5, and so the fifth harmonic is just 1000 Hertz. There we go. Two strings made from the same material are fixed at each end, and both are under the same tension. The first string has a length L1, which is 1 meter, and is being driven so that it oscillates in a transverse standing wave mode with a frequency of 400 Hertz. The second string with length L2, which is 1.18 meters, is also oscillating in a standing wave mode, but with a slightly lower frequency. An observer notices that the standing wave on the second string has one more node than on the first string. The observer hears 4.5 Hertz beat as a result of the combined sound coming from the two standing waves. Calculate the number of nodes present in the first standing wave. So first things first, we see that the observer hears beats, and therefore F1 minus F2 is equal to 4.5 Hertz, right? Because the beat frequency is the difference between the two frequencies. We also know that N2 is equal to N1 plus 1, because the observer notices on the second standing wave that it has one more node than the first standing wave, and therefore as L is equal to N lambda over 2, this is because we have nodes on each side, and therefore this is a half wavelength situation. Therefore our L1 is equal to N1 minus 1 lambda 1 all over 2. Therefore our lambda 1 is equal to 2L1 all over N1 minus 1. So this is the number of half wavelengths in the first string. And so therefore, as V is equal to F lambda, our V1 is going to be equal to F1 lambda 1. And so our V1 is equal to 2L1 all over N minus 1 times our F1. Now we can do the same process for our second string. Our wavelength in the second string is equal to 2L2 all over N2 minus 1. Now again, as our N2 is equal to N1 plus 1, N2 minus 1 is equal to N1. So we can make that substitution right here. And therefore our V2 is equal to 2L2 all over N1 times our F2. Now our V1 is equal to V2. The reason for this is because they are made of the same material and have the same tension. And so therefore our V is equal to the square root of the tension over mass per unit length. If they're made of the same material, they will have the same mass per unit length. And as they have the same tension, they're obviously going to have the same tension. And so the velocities will be equal. And so therefore, 2L1 all over N1 minus 1 times F1 is equal to 2L2 all over N1 times F2. We can make this slightly simpler by bringing the frequencies up top. You don't have to do this, I just prefer like this, my personal preference. Okay, so we can divide both sides by 2 to make it more simple, and we get L1 F1 all over N1 minus 1 is equal to L2 F2 all over N1. Now we can cross multiply, and we get N1 times L1 F1 is equal to N1 minus 1 L2 F2. So we have N1 L1 F1 is equal to, expanding this out, we get L2 F2 N1 minus L2 F2. Now gathering our like terms, so gathering all the N1s together, we can move this to this side and move this to this side. And we get L2 F2 is equal to L2 F2 N1 minus N1 L1 F1. Taking out N1 as a common factor, we get L2 F2 is equal to N1 L2 F2 minus L1 F1. Now dividing both sides by this right here, we get L2 F2 all over L2 F2 minus L1 F1, and that's all equal to N1. Now we can plug in our values. We know that L1 is equal to 1 meter, L2 is equal to 1.18 meters. We know that F1 is equal to 400 hertz, and therefore, due to the beat frequency, we know that F2 must equal to 395.5 hertz. There we go. So now plugging in our numbers, we get 6.998, and that's equal to 7, rounded up. So that means N1 is equal to 7, and so therefore there are 7 nodes present in the first string. There we go, and we're done.